Hi all. This is the last exercise of chapter 7. So we're gonna look briefly at the families of functions, a little bit of mixture of everything from chapter 2 to 6, and one of the application is to solve literal equations. So it has a mix of rearranging formulas, simultaneous linear and nonlinear equations. Alright, so examples of family of functions will include linear functions in that form, polynomials of different orders, okay, also exponential with we've seen also different types of transformations. Those ones are two types of dilations that might involve mapping with the use of original and image coordinates, as well as a matrix notation. Here is an example of the you have a function that is a quadratic. As a is a parameter which is non-null, that will create a family of parabolas. They will have a vertex which is common at the origin, and depending on the value of a, as a increases, you will go let's say for a positive value will be that trend, and as it will be negative and get smaller, it will go towards the blue one downwards. Okay, so there's a few properties you need to be kind of determining as you go, depending on those parameters. Let's go on with a few examples. Here you have a family of straight lines of that form mx plus 2. Notice that m is an element of r plus, so it's from 0 excluded to positive infinity, and you have a series of questions. So with part A, find the x-axis intercept of the graph. So you make y equals 0, you solve for x, you can do that by hand or on your CAS calculator, and you get an expression, a formula for a the x-intercept, and it will be dependent on the value of m. Next one, for which values of m, so notice values, so it will be an interval or different values, is the x-axis less than -2. The less than -2 will introduce an inequation, so we'll set this inequation. That's my x is less than -2. We replace x by the expression that we had before, we solve for m, and we end up with m is less than 1. We also know from the start that m is from 0 to positive infinity, so the values of m will be a real value from 0 to 1 excluded. To find the inverse function, you swap around the variable x and y and make y the new y the subject. You end up with this equation, and not surprisingly, it is also a straight line. The domain is also R, as the range of R, the f is also R. Okay, so yep, find the equation of a line perpendicular to the graph of y equals f of x at the point 0, 2. So for the line to be perpendicular, looking at the original gradient of the function, which is m, the product of the gradients of two lines that are perpendicular is equal to -1, so the perpendicular line must have a gradient of -1 over m. We rewrite the equation with the gradient and the coordinate of the point that belongs to that perpendicular line, and we rearrange to make y the subject, and this is the new equation. and that's example 11. I must in a way. Anyway, you have this example in your book. Okay, so you can see this bit. Next example. So you have a graph of a quadratic function. It passes through 1, 6 and 2, 4. Find the coefficient of the quadratic rule in terms of C. So we're going to we need to determine how C fits into the quadratic. It's in the form ax squared plus bx plus c, so that's your constant term or your y-intercept. So as it is written, we have 2 points, 2 equations. As we have 3 unknowns a, b, c, we can only have a parameterized form and not a unique solution. So here the decision has been made for you to make c the common parameter. So we need to express a and b in terms of c. So you end up with those 2 equations. What we need to do is eliminate or substitute a or b, okay, as we want to keep c as a parameter. And we end up with those 2 expressions of a and b, and we can substitute that back into the final quadratic equation. So now the quadratic equation here, as c is a parameter, is a family of parabola. Okay. Yep. There's another example with exponential. I skipped that one. You can look at example 13. Now I'm going to look at example 14. Quite useful at this time of revision for the first SAC. It will involve transformations, and this is just a nice review of the mapping and the matrix notation. So here you have your matrix notation. Your xy represent your coordinate of your original point of the curve, and those are the image coordinates. The function that you transform hasn't been defined yet. This is just the mapping and to relate for the transformations. Dilation of factor 5 from the y-axis, dilation of factor, is that, yes, k, from the x-axis, and those are your respective translation, horizontal and vertical. Find x and y in terms of x prime, y prime. So you will do matrix operations, so multiplication and adding, and you will get those 2 equations. You make x and y the subject, and hence we have those 2 equations. We're leaving x and y as a subject for part B, as we know the equation is that we need to transform is y equals 1 over x. We substitute those expressions and we make y prime the subject. We end up with this equation, and the primes have been removed. Okay, so we end up with the new transform hyperbola. Okay, and we're going to use this equation to find part C. So with part C, that image needs to pass through the origin, which coordinates are 0, 0. So you substitute x and y by 0, and you find the value of k to be 2. Alright, and that's it for today. So see you later.